Good day, everyone. Today I want to speak with you about substitution and elimination mechanisms. So these are going to be multi-step mechanisms. Some of the ones that I'm going to go over in the beginning are going to be just kind of in one shot. Some of the bimolecular mechanisms I've already kind of pointed out to you in the previous module, or submodule rather. Just for a little bit of a review, if you want to cut ahead to some SN1 or Chapter 8 material, you're more than welcome to do so. I'm just going to kind of review some of the things that we went over the last time. So the first is going to be SN2 mechanisms. Remember that the rate law is going to be equal to the rate is equal to K times the concentration of the nuke times the concentration of the electrophile, right, with a leaving group. Okay, so just a generic mechanism here. You're gonna have a nuke, and you know what? I'll actually do a say OCH3, so methoxy group. And I'm gonna have that as my nucleophile, and then I'm going to have, let's say, this is my substrate. So I'll have my leaving group be, let's say chlorine, just for convention's sake. Then I'll have hydrogen up above, and then let's say, whoops, in the background I'll have CH2, CH3. Okay, so this is going to be a secondary substrate. So now I'm just going to do everything in one fell swoop. Remember that with SN2 mechanisms, there's no time for any kind of rearrangement or any carbocation reconfiguration or what have you, or rearrangement. There's simply just going to be one shot with a transition state. Okay, so that chloride anion is going to pop off, right? So it's going to be a stable anion since it's a full octet. And then you're going to have another group here in place of chloro group, which is going to be your substitution. Okay, so we'll again talk a little bit later about why that's such a reactive nucleophile, but let's cover our bases here and talk about E2 mechanisms. So really the rate is going to be equal to K times, instead of nuke, you're going to have a base concentration. Okay, so these are going to generally occur under basic conditions, right? And if you really want the distinction for how these are going to occur under aprotic solvents. So just note that, and we'll get into that a little bit later on in the module. By the way, this is going to be a very long module, so if you want to skip on over to some of this stuff in Chapter 8, I don't blame you at all. I'm just kind of recovering this material here. Okay, so OH is a sort of a textbook example of a base here. So let's say we have CH3 here, we have hydrogen here. Okay. Put a chloro group here. And then in the front, I don't know, we'll say we have another CH3 group. Okay, so just remember that this hydrogen that needs to get plucked off and this chlorine need to be anti to one another in order for an E2 mechanism to transpire and you get the right stereochemistry. So it's all going to happen in one fell swoop. It's going to be a cascade of electrons. You're going to form water. So Cl minus is going to leave again, just like before. So pretty classic textbook example of a leaving group. Then you're going to have water and your alkene, which is going to be something like that guy right there. Okay. Now, so this would be your conjugate acid of your OH that you started out with, which again is a strong base. So let's go through a couple of the exercises that you see in your text here. These are particularly for biomolecular elimination, so we'll keep this E2 general mechanism above, and we'll attempt these other problems in your notes. So if you want to look at problem 729 on page 357, a few of those examples I have laid out for you. I'll draw those up here. So again, this is just going to be E2, so biomolecular elimination. So let's say we have chloro group right here. Then we have a hydrogen. And we have a strong base like NH2 minus. Again, we need a strong base in order to initiate this elimination. Okay, so something that's going to be a weak base is not going to fly in terms of this kind of mechanism. It would usually result in unimolecular, which we'll get into later. Okay, so effectively what you're going to get here is a double bond, tri-substituted. There's not going to be any stereo specificity here because you have these two methyl groups sitting right there. Okay. All right, now for B, or sorry, that was B, I guess. You have this other example where let's say you have an iodine group, okay, and then you have NaNH2, which is again a strong base. So I didn't write the sodium there. The sodium is just going to be there to balance the charge. And I guess you could have it there if you're super type A about everything. Okay, so again, you're going to have a carbon that's alpha to the carbon where, or sorry, a hydrogen alpha to the carbon where the leaving group is going to be. So in other words, we're in good shape here. And all of these are going to be the same, so it doesn't really matter. So this is going to be a methyl group sticking off here. It's kind of giving you a little bit misleading from the hydrogen that's sticking out there. But you also have to remember that you have to have a complete octet up there. So now that this hydrogen has been removed, it's going to be more acidic from that iodine pulling electron density away because it's slightly electronegative. These electrons are going to come in and basically establish a double bond and kick off that iodine leaving group, which is going to be actually a formidable leaving group in biomolecular conditions, as you'll see. Okay, so the I minus leaves. You have NH3, which may go up into the gas phase depending on what temperature this is at. It'll probably be at an elevated temperature, hint, 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 for elimination. So you will get a geminal alkene as your product, and you'll also get NH3. And that would probably be in the gas phase. And same thing goes up here. Okay. Now, if you take a look at the next step, notice how I didn't have any coordination in your notes. That's to suggest that there is not alpha hydrogen to pluck away to perform an elimination, so that elimination will not occur. So if you have any questions about that, please be sure to see me during office hours. Kind of have to keep things moving along here. Okay, so let's get into unimolecular conditions and stability considerations. So this is where kind of everything comes together. Even though this seems to be a lot of information, this is a lot of information that I've already kind of hinted at throughout the course thus far. So in other words, these next two chapters are really going to be essential for the rest of the course. Okay, so we're going to look at unimolecular conditions. So okay, so if you recall your carbocation stability and how there can be some rearrangement. So we have CH3, it's going to be least, followed by, let's say, secondary. Now I'm going to do line drawings, guys. I have to kind of keep it straight into the point here. Okay, so it's secondary here, primary here. Okay, and then we have tertiary carbocation. So this is going to be most stable. So in other words, something that you're going to see that's going to form a tertiary carbocation is going to most likely be a unimolecular mechanism. We'll get into some substrates and where that kind of intermediate will form. Okay, so can any carbocations rearrange? Of course, you've seen this example already. Let's say we have this guy right here. Okay, so we know that this is going to be second to least stable. So in other words, we have a neighboring carbon right there that still has a hydrogen attached to it. And again, we're looking for the target that is most stable. So if we do what is referred to as a hydride shift, remember I'm going to have to shorthand that as tilde H. Okay, so it means that hydrogen slides with its 2 electrons and satisfies that octet over there on the terminal methyl there. And then you'll have a more stable carbocation, most stable, like right there. Okay, so there's other rearrangements that you can consider as well. So right here we have a secondary carbocation. Okay, and then we have our chicken foot here. Now, there are no hydrogens here to slide over and stabilize that charge and have a tertiary carbocation over there. Conversely, we can't have a hydrogen to slide over here, or we're going to go to something even less stable, so that's not going to fly. So in other words, we're going to have some sort of methyl shift. Okay, so instead of tilde H, I'm going to have tilde CH3. And then that's going to satisfy the octet of that secondary carbon. And now we're going to have a tertiary carbocation to the right. Okay, so that's just some rearrangement going from least stable to more, or less stable to more stable carbocation. Okay. All right, so let's just pick apart some examples here. which side is most stable, left or right. So if you look at problem 7.20 in your text, page 349, we can go over those real quick for you. Pull that up. Okay, page on 349. Okay. So I had to throw resonance into the equation here. I'll just keep that up. Remember, this is all going to be under unimolecular conditions, so that means the base or attacking group, its concentration is irrelevant. Okay, so I'll give you a couple minutes. I'm going to draw these out. I'll just write pH here. We know that it's going to be representative of a phenyl ring now, right? Okay, so which side is going to be more stable here, on the left or on the right? Then we also have okay, they have the hydrogen depicted, but I'm not going to depict it. Okay, so secondary carbocation to a tertiary carbocation. This is secondary, so see what you come up with for those examples. Just pause a minute. Okay, so notice how it's secondary here, secondary here. If it conjugates with this particular pyrite system that's a phenyl group, then that means that it's going to be more stable closer or just off of that sp2 construct, because remember that all of these carbocations are sp2. Okay, so all sp2 hybridized. All right, so what happens here? It's a methyl shift. Right. So that's what you're going to see there, and that's going to be a more stable secondary carbocation via resonance. Okay, so again, this is going to be a hydride shift. Okay, so we're going to go from this tertiary carbon over to the secondary carbocation to satisfy the octet there, and then we have most stable tertiary carbocation right there at the junction of the ring. Okay. So take a stab at problem 7.36 and see what kind of methyl or hydride shifts you can come up with for B, E, and F, those particular examples. Okay, so I'm going to expound upon some keto-enol tautomerism a little bit here. And I'm going to revisit, well, something somewhat analogous to what you saw last time we spoke about this. Instead, I'm just going to have a dial, not dial it in. Alright, so remember that these electronegative CO double bonds are going to pull electron density away. So it's going to stabilize a negative charge that would happen if you, or would occur if you had a base to strip off one of these hydrogens. So let's say, for the sake of argument, we have just regular old water to be around and serve itself as a base. Okay, so pushing some electrons around, we have so we have a negatively charged enolate. That's going to pick up hydrogen from hydronium ion. Then you're going to have, those lone pairs are going to be kind of a giveaway here. You're going to have intramolecular hydrogen bonding. Okay, so with that said, you're going to form a pseudo six-membered ring. One of those lone pairs of the CO double bond oxygen coordinating and kind of holding that hydrogen in place, so it's going to be pseudo six-membered ring. Okay, so typically 5 and 6-membered rings in nature are most abundant because they're the most stable. Okay, so that's something to think about with keto-enol tautomerism. And notice how this wasn't under any type of acidic or basic conditions. It was just under neutral conditions in the water. Okay, so something to think about when you, let's say, generate an enol product and it's going to have to revert to a ketone or something like that. So this kind of chemistry, while you don't you think, well, how is this relevant to mechanisms? Believe you me, it will be important later on. Okay, so now I'm going to go over some multi-step mechanisms, and then we'll get into some unimolecular, kind of expound upon that and go through everything step by step. So problem 7.56 in your text on page 363 has a particular reaction with this substrate, which is an alcohol. So it's not a very powerful nucleophile, but we have a very strong acid here, and we have a not very good base, but this definitely compensates for it. So we're going to form some kind of intermediate here. Okay. And it's going to be OH2. So the question here is this going to be a good leaving group? Actually it is, because if you really think about it, if this were to take these two electrons with it, it's going to form something stable, something much more stable than OH2 minus with an alkyl group hanging off of it. It's actually going to form water. Okay, so remember that Cl minus, it's going to be hanging out right there. Right, it's going to be quote unquote leaving from that hydrogen getting dumped off. Is going to actually behave as a nuke and boot off this water molecule. So you're going to have water kicked off as a result, and then you're going to have a substitution, bimolecular substitution, with Cl taking the place of that protonated alcohol. Okay. So it's just the two steps that they talked about above and below that reaction arrow. So they're talking about different steps. They're not talking about adding more reagents, which is typically what you do if you number things above and below a reaction arrow. Okay, so let's go with a more I guess multi-step sort of theme here. So 7.59 on the same page. Problem 7.59, same sort of convention here, but there's going to be 4 steps instead of 2. So this is 2 steps. 7.59 is going to have tert-butoxy ether, asymmetric ether. Okay, so it says proton transfer involving H3O. Okay, so this needs to pick up hydrogen from H3O or a hydronium ion. Okay. So you're going to have a protonated species that's going to be very unstable. So, in other words, some bond breakage has to occur to stabilize and make other products. So, in other words, heterolysis needs to occur. And heterolysis, that just means that it's taking some electrons with it, 2 electrons with it, and stabilizing or initiating some sort of charge separation. Now, in this case, it's going to be a conservation of charge because notice how we're going from positive to positive. Next is going to be positive. So this is leaving off as a T-butanol group. Okay, so now we have a stable carbocation. I'll just shorthand that with a pH there. Okay, and then positive charge right there. Okay, so it's not going to rearrange in any way. It's not going to go within the ring because these electrons are whizzing about at a high speed. So coordination involving water, right? So what's left back here is going to coordinate. Then you're just simply going to have some kind of proton transfer, right? Because once you coordinate here, you're going to form a another positively charged species. Okay, so that is going to be the sucker right here, positively charged again. So now, so you can't really see that. There you go. Okay, so if another water is around to pick that off, right? Because remember that water, if it's going to be H3O like that, there's going to be an abundance of water as well that's going to be around. So it's going to be the solvent. So now you're just going to have what is referred to as a hydrolyzed product. So you're stripping off that ether and essentially replacing it, stripping it off from this bond here. Moving back, sorry. Right here, and I'm replacing it with a hydroxyl group. Okay, so just a conceptual question for you to think about later. Since we had that sp2 carbon right there, are we going to have stereospecificity on this particular product? The answer is no. We're going to have a racemic mixture. We're going to have a little bit of S and a little bit of R. So bear in mind that when you're dealing with unimolecular mechanisms. This is an example of a unimolecular mechanism. So you're going to be under product solvent, okay, and you're going to essentially strip off this ether portion on the right. Okay, so I'll let you deal with problem 7.57 on page 363. That is going to be an electrophilic addition multi-step example, so be sure to look at that and look at the previous module where I kind of lightly introduced elimination, electrophilic addition. Okay, so from what I'm going to be going over with you for this next, I don't know, maybe hour or so is going to be how certain molecular, mechanisms occur. So basically what Chapter 8 covers. What Chapter 9 covers is going to be more of how, okay? Or, sorry, it's going to be more why, not how, okay? So we haven't discussed unimolecular mechanisms or kinetics really in great detail. So bimolecular substitutions and eliminations are going to happen in one step. And then 2 or more steps. Are unimolecular. Okay, so that's some. So both have rate determining steps, right? Or energy hurdles they have to jump over. Okay, so we're going to draw a unimolecular energy diagram on the left here. Okay, so with increasing energy going in this direction. And this is just going to be some generic reaction coordinate. So RxN is just shorthand for reaction. Okay, so if we have unimolecular on the left, that means that, let's say we have I'll do that off. Okay, so which one of these steps is going to be the rate determining step? The one that requires the highest energy, the biggest hurdle to get over. So notice how once you get over that, you're pretty much home free. So this step may just be like a proton transfer or something like that. A second step might be heterolysis, where you have to actually, there has to be enough energy there to separate charges out. It's like trying to pull a magnet from the fridge, right? You're going to see some resistance unless you really crank on it and try to pull it off. Okay, so this would be unimolecular. Bimolecular is going to look like this. Again, energy going that way. Once again, reaction coordinate. Okay, so really there's just one hump to overcome, right? So in other words, there's really no time to seesaw and second guess and backtrack and what have you and fall back to your default. You're either getting over the hump or you're not, right? So there's always going to be some kind of energetic barrier no matter how favorable the reaction is. So right there, it looks somewhat definitely favorable, seeing as it's going from a higher energy state to a lower energy state, right? So that's something to think about. But what you see right here in terms of activation energy going from, the energetic standpoint of your starting material all the way up to that transition state. So that double dagger that I showed you is going to be right up there. Okay, so the rate determining step and the transition state complex are going to be right there at the top of the peak. Okay. All right, now let's get into an SN1 mechanism or a unimolecular substitution. If you were to write the rate law for this, you would just write rate is equal to K times your substrate. Okay, so in other words, in a unimolecular mechanism, notice how if you just have this here without any, not coefficient, but exponent, that means that it's just going to be first order. Okay, so in other words, no matter how much base you have there, be it weak, it is not going to affect the actual rate of the reaction, right? You still need some there, but in terms of trying to crank out higher and higher concentrations of, let's say, methanol in this particular instance, it's not going to make a difference. It's not going to change the rate of the reaction. Okay, so now we have methanol in the presence of 1-bromo methyl cyclohexane. Okay, now here's the issue. We can't just have or expect this methanol to just come in like Grant took Richmond and just push everything off, right? This is going to be really bulky. If you remember some of the things you learned from conformers and things like that back in chapter 4, you're noticing that things are very clustered and bulky, and there's really not much room for any type of reaction like you'll see with a bimolecular mechanism. Okay, so you saw some secondary substrates, and you'll see some primary substrates as well. But in this particular case, this is, you can think of it like sort of the more gentlemanly reaction, if you will, right? So you're going to wait for this other fellow to leave, right? So in doing so you may wait around a year or two, not really rock the boat with your, or with the potential mate, whatever, right? So you're going to kick off, or you're going to wait for bromine to make his own exit. Right? Meanwhile, you're just kind of playing your acoustic guitar and hanging around, or this OCH3 is hanging around, this methanol is hanging around, and then finally, here's this carbocation. It's all ready to hot and trot, and it's ready to date because Br- took his stuff and left. So methanol says, here's my shot. So I can come in through the front door or come in through the back door. Take that for what it is. Coordinate. And notice here how there is a positive charge throughout everything following heterolysis. So this is the heterolysis step. Okay? And then this is the coordination step. Okay? And then lastly, this is just the proton transfer step. And so methanol is just going to act as a weak base here and pick off this hydrogen. Then you're going to have a stable product. So, what's to be learned here? Let's start off from the top. This is going to be leaving, this bromo group is going to be leaving, forming a tertiary, a stable carbocation. So you can think of that as a good catch, right? It's kind of not going to go off and do anything weird. And then this not so radical guitar playing methanol is going to come in and coordinate to that positive charge, and again that can come into the plane of the into the plane of the board or out of the plane of the board. So you're going to have a 50-50 mixture, but that's not going to matter because you don't have a stereo center about this ring. If this were substituted somewhere else, then you would have a mixture of products. Okay, but these are all going to be the same product in the end. This last step is just going to be proton transfer, so H plus transfer. And there you have it. All right, now we're going to go over unimolecular elimination. Okay, so once again, we're going to have to wait for heterolysis to occur. So a bromo group has to leave. Okay. So we've initiated some charge separation through a protic solvent. Hint, hint. Okay, so now we have a positive charge. Can it migrate? Not really. Won't. It'll be counterintuitive for a hydride shift to happen here. Maybe there'd be a different substituent hanging off of there. It'd be a different story, but for now, we're good. Okay, so we're at a positive charge. We have quite a few different hydrogens in which a deprotonation can occur. And we don't have the world's strongest base here with water, so we have to kind of weigh our options here. We could form a double bind by right here by removing this hydrogen. We could form a double bond here by removing this hydrogen. We could form a double bond here by removing this hydrogen. So in essence, you could form 3 different products. Okay. Now, we'll kind of weigh our options here. Say water takes this one first, right? So that's going to lead to, I'm going to draw this really small. And okay. So there's one option. We'll say the second option is water taking this hydrogen, and these electrons cascade down to form the double bond right there. So you're going to get tetrasubstituted alkene, and then you're going to, from stripping off this hydrogen with water, okay, these are going to cascade down, and then you're going to form a geminal alkene, which is going to be actually least stable of the 3. Okay, so which one do you think is going to be formed in most abundance? One that's going to be formed in most abundance is going to be the one that's the alkene that's going to be most substituted. Okay, so in this case, this is going to be what is referred to as your Zaitsev product. We'll get into that a little bit more later, but now we're going to get into some review with concentration effects and how they may change the kinetics of a particular reaction. Okay, so I'm going to kind of breeze over some of the math here involved with this problem, 8.39. So 8.39 on page, I don't have the page on there. Let's see, pull it up here real quick. 8.39 is on page 435. So the data says that if you're going to compare, you want to have a constant. So in other words, if you want to see what that particular ether concentration has, in other words, a substrate, you're going to want to see how much that affects the rate if you double it and you keep the water, for instance, at the same concentration. So we'll say experiment 2 over experiment 1. Okay, so that means if we have 0.020 molar of our ether substrate over 0.101 molar ether. So in other words, between experiment 1 and experiment 2, you've doubled that concentration of ether. And we need to figure out what that particular exponent is going to be. So we'll put M here. Right? Not to confuse you and say that that's going to be the molarity. That's not the case here. Water is going to be fixed. So in other words, if water is 0.45 molar, whoops, dyslexia, all going to zero out, right? Because you're just going to have, that's just going to be 1 in that particular term. So 1 times whatever is going to be 1, right? So notice that if you divide the rate of experiment 2 by that of the rate of experiment 1, it's going to be twofold, so we'll just put 2 right here. So in other words, 2 to the m power is going to be equal to 2, so that means m is going to be equal to 1. Okay? So 2 to the m power is equal to 2, m is equal to 1. So in other words, it's first order for the ether. Okay, now for the next one. So by doubling the concentration from experiment 3 to experiment 2 for water, we can see that we don't even have to do the math, right? If we double it, you notice that the change in the rate is nothing, right? It's still going to be the same. So in other words, water is going to be to the 0th power, right? So in other words, it's going to be 1 just like it is right here. You're not going to have any change in the kinetics by doubling water, tripling water, quadrupling water. Okay? So that means that the rate, we're going to write a rate law, is going to be equal to K times R OCH3, or the ether, and that's it. Okay, so this is not going to be expressed in the rate law, is what I was trying to get at. So in other words, it's going to be unimolecular. Ding. Okay, so now that I reviewed with you some of the math that was involved in establishing whether something was unimolecular or bimolecular overall, giving you a little bit of PTSD, or reminded you of some of the awful math you had to do last semester, let's get into some things that affect rate. Well, we already know that concentration affects rate. Okay, so 1 is going to be concentration of whatever. Reactant, of course. And then catalyst. So if you have metal catalyst, acid, base, catalyst. So sometimes you need a little bit of a small concentration of acid or base to make a reaction go forward. And, like I said, with chemistry, it's not always a matter of if, it's more a matter of when. So, the more efficient you are at speeding things up and getting them to go efficiently, the better off you'll be. So time is money, etc., etc. All right, next is going to be temperature, but, so in other words, temperature is going to change what? The reaction rate constant, right? K. So that's going to change K. Excuse me. So temperature, if you elevate a temperature, it means you may see a reaction going faster, especially an endothermic reaction, right? So something that needs some heat energy to move forward into the right direction. And of course, Perle-Chatelier's principle, which is also related if you change other state functions like pressure. Right, so some things can be done in a vacuum, and you can have a higher yield as well as a volume. So sometimes, if you have a very large quantity, you're going to have much more stuff to kind of mix around and have everything collide, right? You need collisions in order to make a reaction successful. Okay, so let's think about now the stereochemistry of some of these products. Okay, so a unimolecular mechanism, they're going to, so let's say SN1 and E1. E1. There we go. Okay, so you're going to yield a mixture of product. So let's say you'll have different alkenes from E1, like we saw before, right? So we have some major and minor products, some more thermodynamically stable than others, and then for SN1 you're going to have a mixture, a racemic mixture of R and S, right? You still have that carbocation intermediate that's flat like a sheet of paper, either into or out of, right? Okay, so then with bimolecular mechanisms, so SN2 or E2 mechanisms have a yield inverted or E alkenes respectively. Okay, so let's say something was optically active and it had R for the substrate of SN2. When you react things out, and it does go through SN2, and you have a strong nucleophile to push that leaving group off, it's going to revert to S, right, and vice versa. Okay, so for an E2 mechanism, it's going to form something that's already going to be E, or on the opposite ends, right? Because you have, remember, you have that sort of conformation of that hydrogen that's going to get stripped off, that protic hydrogen, and then that leaving group that's going to be alpha to that. Okay, so it's almost like a staircase. Okay, so let's figure out what the products are for each one of these steps now, or each one of these particular reactions. So this is going to be SN2. This is going to be SN1, this is going to be SN2, this is going to be SN2, this is going to be E2. Alright. So with an SN1 reaction, remember that heterolysis step has to leave first, so you're going to have a carbocation intermediate. So in other words, you're going to see a mixture of R and S. Products. Okay? So in other words, there's a 50-50 chance that that OH is going to coordinate on either side of that carbocation intermediate. I'm moving over here to the SN2 mechanism, or reaction. This OH is going to attack without the occurrence of heterolysis. It's going to boot it off, and it's going to be on the other end. So in other words, it's going to be an inversion, or an inverted product, which is going to be this form. So instead of being a wedge sticking out like the substrate, it's going to be a dash going in as a product. Okay, for SN2, for the bottom example. So remember that this OCH3, which is going to be your nuke, is going to come in on the opposite end of where that CH3 group is, right? So in other words, it's going to have to kick off this particular bond, right? So this is kind of a strained bond angle, if you will. So that oxygen is going to want to take its electrons. So it's going to go from a negative charge to another negative charge, and you will have this guy as a result. Now, presumably, you would have some kind of proton or Bernick solvent here to protonate this particular alkoxide. Okay. I'm missing some carbons here. Sorry, I boot that. Okay, 1, 2, 3, yeah. Missing a carbon there. So, since there is this CH2 here, you're still going to have some stereospecificity, but just remember that, let's see here, so, well, in other words, you're not going to get a mixture of products anyway, because remember that you have the CH3 here and this CH3 here, so there's going to be some symmetry involved. So you're going to get one type of particular compound. I'm just trying to visualize in my head here. Let's just say this is sticking out. And this methyl group continues to stay in. So this is about the same plane. Right, so we'll say we have a hydrogen right here. So there's going to be a hydrogen, let's assume, right there. Now for the trickster, over there on the right, that E2. So you say, oh, well, we want to form our most stable product, which is right here. Well, that's not going to be the fastest product that's going to occur, because if this bromo group is going to be sticking out, we have to have a hydrogen to be removed from the strong base sticking inward. Well, that's not there. CH3 group is there. So in other words, we need a hydrogen that's going into the plane of the board here. It's going to get deprotonated to fall over and with its electrons and kick off that bromo group. Okay, so in other words, you're going to get this product instead, which is going to be stereospecific. Okay, draw this a little bit better. There you go. Okay, now I'm going to begin a tale of two different types of species that want to kind of fight for the same carbon here. So we're going to go over nucleophiles as well as leaving groups. So there's going to be this ever constant struggle of one versus the other if you're talking about a particular reaction that's reversible, or some particular reactions that are irreversible where the nucleophile is much more powerful than the nucleophilic capability of the leaving group. Okay, so in other words, whichever one is going to stick more is going to stay more, right? So let's go over some different types of bonding examples from the beginning of the text. Remember in chapter 1 I kind of emphasized looking at those carbon whatever bonds. Well, that's going to be particularly relevant here. Now, if we think of CC bonds are going to be right there at 339 kilojoules per mole. Okay. Then, say CBr is going to be 280 kilojoules per mole, so it's going to be demonstrably weaker. Then you have CO. Excuse me, it's going to be 351 kilojoules per mole. And then let's say CC from an alkyne, right? That's still going to be 339 kilojoules per mole. Now I'm not referring to the CC triple bond, that's going to be much higher. course, as you stack on more bonds, higher bond orders, clearly the higher the bond dissociation energy is going to be. But let's think now just about sigma bonds here, because these are the bonds that are going to keep these leaving groups and these nucleophiles on or off, right? So it's not particularly linear in terms of what we're looking at here. So CC carbon bond, while it seems like sort of in the middle between what we're looking at between carbon and oxygen and carbon and bromine, is that the issue is that we really have, let's just treat this as an aliphatic carbon. So that means there's just an alkyl chain, right? There's no double bonds or triple bonds like you see here down at the bottom. This is going to wedge itself somewhere in between CBr and CO single bonds in terms of magnitude of bond dissociation energy. But think about what you're going to have in terms of a difference here. This would be, let's say, an sp3 sigma bond, hybridized sigma bond, as opposed to an sp sigma bond. So an sp sigma bond is going to be more stable because you have a little bit more of an S character as opposed to a slightly diminished S character from sp3. Okay. So remember, this is going to be 50% S here, and this is going to be, if this were tetrahedral, again, sp3 hybridized, it's going to be 25% S. So a double stability, if you will. Okay. Now, if we're going back to leaving groups and those kinds of capabilities, where you look at, let's say, carbon to fluorine, carbon to iodine, carbon to bromine, and carbon to chlorine. So these are all halides. Notice that this is going to be the lowest at 238 kilojoules per mole. Okay. And then the highest is going to be CF here, so that's going to be, what, 439 kilojoules per mole. So these bonds are particularly abundant in something like Teflon. So Teflon is pretty much chemically inert, right? You can't really, break it down with base or anything like that. So it's quite a formidable thing to use if you're using to thread let's say a screw or something to make sure it doesn't corrode over time. Okay, so CCl is going to be 330 kilojoules, so somewhere in the middle between those. And then CBr, which is going to be slightly lower at 280, like back over here. Okay, so what you can deduce from that is fluoro group is going to be generally a poor leaving group, right? And then iodine and bromine are going to be some of the better leaving groups that you're going to see. Okay, so does that mean that chlorine is going to be a poor leaving group relative to, let's say, a C minus? No, actually it's going to be quite a good leaving group because it's still going to have a full octet. So a carbanion that's going to be a leaving group is really going to be a tough sell. So that's why some of these bonds are so strong, and we'll see some of those examples in a little bit. But let's keep on working here, and let's talk more about nukes now. So we've kind of tried to talk about leaving group ability a little bit here, but we'll expand upon that a little bit more later. So strong versus weak nucleophiles and bases and their size. So a stronger nuke is going to be charged, right? And the electronegativity is really going to be important. So if something can't stabilize a charge very well, then it's going to be more unstable, in other words, more reactive. So in other words, something like this anion here of carbon is probably going to be quite reactive, right? Let's just say this is an ethylene or an ethyl carbanion that is looking to react readily with something else, and it'll be a good nucleophile. But something like this, which is going to be the conjugate base of diisopropanamine, that is going to be not a very good nucleophile because it's so big, right? It's going to be better suited as a base. So you can think of things that are really bulky bases as just being that, as a base. Nucleophile needs to have room to kind of sneak in for attack, right? If it's going to attack some kind of substrate or a good electrophile, it needs to be sort of a little bit more nimble, right? So if you imagine, some really large thing trying to move at the same speed as something that's much lighter, you're in for a shock, right? So, in other words, something that's a little bit smaller and has better means of traversing about and getting into a reactive center is something that's going to be a better nucleophile. Okay. Now, to look back at a pKa table, to think about how strong or weak acids are, remember that the lower the pKa it is, the stronger the acid. Okay, so, but this is sort of like the way you can think of a substrate. So if something is leaving, you want it to be stable upon leaving, because if it's not stable upon leaving, then that means it's not a very good leaving group. Okay, so every time you've seen leaving groups as I've kind of depicted, even generically, you see that it takes a lone pair with it. So in other words, it needs to be electronegative to some degree. So something like this is not going to be very much very electronegative compared to some of the other things that I've kind of discussed with you. So in general, the more basic the species, the stronger the nucleophile. Okay, the more acidic the species conjugate acid, the better the leaving group. Okay, so HI, for instance, HI is going to have a pKa of around -10. Okay, so its conjugate base is going to be a very good leaving group, right? Just like HCl, just like HBr. You can see the magnitude in which those are going to be strong acids. So the better ability to being an acid and dissociating that way, in other words, a stable ion, the better suited it will be to being a good leaving group. So some of the other examples that I have in your in your notes there, you can kind of take a look at. Don't forget that also resonance stability plays a factor in how good or poor a leaving group is going to be. Okay, so now we're going to go over the Hammond postulate and kind of visit reversibility in a particular mechanism. So remember that with similar types of species that are fighting over the same carbon center, let's say if we have a chloro group versus a bromo group, or a bromo group versus an iodo group, they're going to be fighting over the same carbon to be amended there, and then have something else more stabilized sitting on its own as an anion. Okay, so let's think about the Hammond postulate and what exactly it means. Let's say if we have a very strong nuke, right, and then it reacts with, and these are all going to be I'll say SN2, right? Okay, so that nuke comes in, and you have that transition state. Transition state is going to look more like the reactants if this is a powerful nucleus. Or, sorry, nucleophile. So remember that you're going to have that high energy transition state. Right. But this is going to look more like your reactants. In terms of appearance. Now, one thing to mention about mechanisms in general is that they're all postulated anyway. It's all just things that are theorized, and there's never something that's directly proven. But just like anything in a scientific nature, if you see repeatable patterns, right, you tend to kind of go with it. It's sort of like, oh, hey, maybe my type is dating this type of person as opposed to that type of person. Maybe I like this person with straight hair versus this person with curly hair. Whatever, right? So it's almost the same type of repeatable pattern that you're going to see in nature with one functional group, you know, reacting with a similar type of substrate, similar type of functional group, whatever. Okay? So now we're going to generate our product, right? We're going to have a nuke on the other end there. Running out of space like always. Whatever. Okay. Okay, so it's really going to look more like the reactant. Okay, so if you were to look at an energy diagram, it's going to be very favorable, right? So there's just a little bit where you have to go uphill and then a whole lot of downhill going to a more stable final product, right? So if, let's say, if the nuke is less powerful, then leaving group's ability to leave, then that is going to look more like the product, right? At least the transition state is. I know this seems way more confusing, but it's going to make a lot more sense when you actually put this into some application here. I know this is just generic. Okay. It would help a lot if I actually had some kind of color coding, but I've been told not to do that. So, there we have it. This is not part of the mechanism, these arrows, by the way. Okay, so we undergo a transition state again. Don't forget that double dagger. So that's going to be what's sitting atop the transition state at the activation energy hill there. Okay, so it's going to look more like the product. So in other words, going to look like what should be on the other side, right? Okay, so you're going to have the same generic product both times. But again, you have to think about how strong the nucleophile is to how great or poor the leaving group is. And that's really going to give you the distinction. So you have to think of some of the things that I previously spoke about, which were how small or how non-electronegative a particular negative charge's nucleus is. It's going to be coming in to coordinate, right? So how a nucleophile would do, and then how great or poor a leaving group is going to be. So if it's going to be a ion that's going to be highly conjugated, negative, then most likely that's going to be a great leaving group, right? If it has some ability to resonate, etc. Or if it's going to be a stable anion like chloro groups or iodo groups, things like that. So this is going to be a comparably unfavorable reaction, right? So it means it's going to have to climb up a big old hill to get over, and it may just need to revert back to being reactant, right? So we can think of this as, let's say, some kind of iodo group or chloro group trying to boot off OCH3 or something like that. So if you're to reverse things, you would think that, oh, an OCH3 group is going to be a good nucleophile. It's going to boot off an iodo group, no problem. So it would look a little bit more like that. So it's kind of wearing the shoe on the other foot, driving in reverse, whatever you want to call it. Okay. So this is to denote that things are going to be unfavorable if the nucleophile is less powerful and you have a poor leaving group. This is going to be most favorable if you have a strong nucleophile and then you have a great leaving group that's fit to leave as opposed to stick onto that hydrogen. Okay, so when we're talking about concentrations, when you're talking about unimolecular mechanisms and bimolecular mechanisms, no matter whether they be substitutions or eliminations, they're always going to be a nucleophile or base concentration dependent. Okay, so they're always going to factor into that rate law and hence the rate. Now, no matter which type of mechanism, whether it be unimolecular or bimolecular, elimination or substitution, that substrate has to be there. If the substrate's not there, there's nothing to manipulate or rearrange or what have you. So the strong bases, or in other words the charge bases or charge nukes, tend to drive faster rates of reaction. So in other words, there's like I said before, with a faster rate, that means there's less time for any type of rearrangement, even though those rearrangements do happen at a fast rate. Okay. So weak bases and nucleophiles are less aggressive and less intrusive, therefore their concentration isn't that important. So weak base, weak consideration, right? Strong base definitely has a factor in the kinetics of a particular reaction. So the ability of a leaving group. So let's draw some heterolysis steps here. So this is going to be a secondary carbocation and then Cl minus. Right? So this is kind of stable. This is very stable. How about iodoethane. If this were to heterolyze, what are we going to have? A primary carbocation, which is going to be quite unstable. So therefore, this would be a better substrate for bimolecular substitution. Okay. Now, let's pay attention to what we have here with this tosyl group. So a tosyl group is going to be very much resonance stabilized, as you'll see. Okay. Now, if this is to leave, the charge would be formed here. So you would also have a secondary carbocation, like what you see above on that previous example. But you would also have the iodo group here. Sorry about that. Okay, but you're going to have OTS. So that's just shorthand for all of this here. Okay, with that oxygen there at the end. And then you're going to have that secondary carbocation. Okay, so in other words, this is going to be a very good leaving group. If you want to kind of work around some of the resonance structures there, be my guest. This is going to be a very stable anion when it's separated from something else, be it a hydrogen plus, or in this case, this secondary carbocation. Okay, and then the last one to go over here with you is this T-butoxy group. And by the way, the conjugate acid of tosic acid is around -2, so it's a pretty strong acid here. Now this might split off. You have a twofold sort of means of stability here. One is you're going to form a tertiary carbocation, which is most stable. Then you're also going to have this anion, which can actually resonate all around that ring there too. So in other words, this is going to be resonance stabilized, and this may, the conjugate acid of this might have a pKa of about 7. So it's not the world's best leaving group, but it's going to be very much resonance stabilized if things were to break apart. So in other words, that's another example of resonance stability. Okay, so for these 5 substitution reactions that you see here, let's deduce whether they're going to be unimolecular or bimolecular based on what kind of substrates we have. Okay. Now, the first one up at the top is going to be tert-butyl chloride. So that is going to be very much not a bimolecular mechanism, even though we have a strong base here. So that base concentration is relevant. Well, it would be more relevant if it were if the substrate were more accessible. But since this is too sterically bulky, in other words, it's going to be sterically hindered, you're going to have a reaction where you're going to see some heterolysis occur first. So in other words, you have to have a positively charged carbocation intermediate before you have that coordination with OH, right? So in other words, this is going to be SN1. For the second example here, so you have F minus. So F minus in terms of all of the electronegative, and it is most electronegative, it is going to have a conjugate acid that is not going to be as strong as, let's say, tosic acid. So OTS is going to be a better leaving group, and fluorine is going to be more of an attacking group. So in other words, this is going to boot off OTS, and this would be an SN2 reaction or SN2 mechanism, because this is a primary substrate. Okay, so primary and secondary substrates are going to fall into the umbrella of SN2. Secondary and tertiary, most definitely tertiary, is going to fall under the umbrella of SN1. So this is going to be unimolecular. This next is going to be bimolecular. Okay, here's a third one, which is going to be a little less obvious. You have a secondary substrate here, so that iota group can either leave, or NH3 can come in and knock it out. The thing with NH3 is that NH3 is a weak base. So in other words, it's not the world's best nucleophile, even though it can behave as one. But here's the rub. If you think about it, NH3 is going to be, in essence, somewhat of a protic solvent. So it can induce some kind of charge separation. So in other words, you may see some heterolysis here, and you may see some rearrangement where one of these methyl groups is going to slide over, and you're going to form a more stable carbocation. So this would actually be SN1. Okay. All right, and next up here, so you have a very powerful nucleophile, and i.e. a powerful base as well. So, and you would want to keep this under cooler conditions. So in other words, you would not want to heat this reaction up. It's going to be explosively exothermic. So this is, if you don't recall, a Grignard reagent. So it's going to be, in other words, that ethyl anion that I was pointing out to you earlier. So it's going to be a very aggressive nucleophile. For every strong nucleophile that you have, it's going to attack something that's secondary or primary as a substrate pretty readily. Okay, so that means if it doesn't have a lot of bulk in its way, then it's going to react out pretty well. So this is going to be SN2. Okay, and then you have OH here at the bottom. Sorry if you can't see that all the way, but OH at the bottom here. So this is a charged compound, or sorry, a charged ion here. So negatively charged, and you have this quaternary amine. Okay, so a quaternary amine could be a more stable tertiary amine of this left, and then you would have a stable carbocation, which would be tertiary in nature. So in other words, you'd have a tertiary stable amine, and then you would have a tertiary carbocation there. So that would amend perfectly with this OH, or the OH would amend to the resultant carbocation. So this would be SN1. Okay, so unimolecular, bimolecular, unimolecular, bimolecular, unimolecular. Okay, so we do have our reactants here. Okay, so we're going to look at them again, but this time we're going to introduce the solvent effects. So see how those particularly drive certain reaction, and see if that kind of falls in line with what we were just deducing, whether something is going to be unimolecular or bimolecular. So for the first one, we're going to have water here. So remember, the protic solvents induce some kind of charge separation. So like I said, sort of trying to pull a magnet from the fridge, right? So for the second example, we'll put acetone. So acetone is an aprotic solvent. So what that's going to do, instead of inducing charge separation, is going to stretch this dipole even further, right? So it's going to make this carbon right here more electrophilic or electropositive. Okay, and then the third one, we're also going to put acetone here. So now, you know, without looking at anything else, without thinking about a solvent, that would have given us the indication like before that we were thinking, oh, this is going to be SN1. Well, now that we have an aprotic solvent, that's going to establish that, in fact, things are going to be working in a bimolecular fashion. So in other words, for protic solvents, that's going to force a unimolecular mechanism, and then for aprotic solvents, that's going to force a bimolecular mechanism. Okay, the third here, so these are going to react readily with something like acetone, so that's not going to work. We're going to probably use, let's say, DMSO. Okay, so something that's inert to attack from this, again, this anion, this ethyl anion here. Okay, so it's going to be attacking this and through SN1. So this is going to, or sorry, SN2. Again, this is going to be a polar aprotic solvent, right? None of those hydrogens are directly attached to an electronegative element comparatively anyway. So SN2, 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 SN1 at the top. Okay. And then the last one, if you're doing this in water, which is again a protic solvent, that's going to stretch that charge separation out. And then OH can amend and form your alcohol in place of this quaternary amine. Okay, so last parameter I'm going to go over with you is heat. So temperature is going to definitely affect what kind of product you're going to get out of a particular reaction or set of reactants. Just like your solvent, as you've seen prior, is going to change what kind of product you're going to form. Whether you're going to have a stereospecific problem or you're going to have a product, or you're going to have a mixture of products. So with DMF or dimethylformamide, that is going to be a it's already written out in your notes as DMF, which is just going to be this. Okay. So dimethylformamide, so like formic acid would just be this with all this with just OH instead. Okay, so first thing you're going to do with DMF is ascertain that this is going to be a bimolecular mechanism, because what is it going to do? It's going to stretch this dipole. So that way this, which is more electronegative and stronger nucleophile, is going to come in and bang into that carbon and kick off that bromo group all in one fell swoop. Okay, so what kind of product are you going to get from that? You are going to get and remember, this is a secondary carbon here. So you're going to have an inverted product. Okay. Now for the second reaction arrow, notice how heat has been applied. So with increased heat, you're going to have an increase of entropy, or delta S. So in other words, it's going to change, instead of having two reactants and two products, because this would also have what? This would also be Br minus, right? So 2 in, 2 out. Okay. For the second example here with DMF again, but with heat applied, you have a different compound as a product. You're going to have this alkene that's going to be formed. Remember that this has the ability to rotate, so that hidden hydrogen that's within that line structure is going to be somehow anti that bromine at some point. Right, so think back to those Newman projections where everything was rotating about. there's ability for that hydrogen to get stripped off in an anti-form, and then, you know, per that sort of staircase L motif, that is all going to happen in one shot. This is not stereo specific anyway, so you're going to get something that's neither E nor Z. Okay, so you didn't have to worry about that particular consideration. Now, for the third example, now we have it under polar protic solvent, so that's going to be different. Instead of stretching this dipole, what's going to happen is this positive and negative charge are going to split apart, right? So in other words, you're going to have a carbocation intermediate. And with the heat, you're going to bring about, so you're going to have some kind of carbocation intermediate that's going to be more stable as a carbocation right there at the more substituted carbon. And you can have major products and you can have minor products. A minor product would be this. Okay. What would be the major product? The tri-substituted, like what you see above there. So remember that resultant positive charge is going to pull electron density away from these hydrogens that are alpha to that particular carbon. So this is going to be major. Okay. All right, and then finally, again, if you're going to have that carbocation rearrangement, what you're going to see is a 50-50 mixture. Again, this is going to be substitution because it's not going to have that heat influence to drive entropy or more products. So remember that you're going to have methanol here, right, as a byproduct, not an organic product, right? And then you're also going to have that group that had left, in other words, Br minus. So something to think about in terms of entropy. So in other words, 2 in, 3 out for both cases there, right? So you're going to have methanol here. Both cases in the middle is what I'm referring to. Okay, and then remember, this is also going to involve a proton transfer, so this is also going to be acting as a base. So let's say we have is that going to be stereospecific? No, it's not, because these two methyl groups are there already. So in other words, it's just going to be that one product. Okay. So it's going to be that asymmetric ether, and again, these two methyl groups are going to be the same. So in order to have any stereospecificity, you need to have 4 coordinates that are all going to be different. All right. So let's go over a couple of examples here. Pause for a minute, and then we'll get into these last 2 within the module, and that should wrap things up for exam 2. Okay, so for these next few problems, I'm going to kind of give you all the different things to kind of think about while you do the mechanism in your own time. But I'm going to give you the product or products that you would expect, and I'm going to tell you what particular type of reaction this is. So the first one at the top here, this is 980. This should be example B. Okay, this is going to be D. This is going to be E. This is going to be F. Okay. Now, the top example for B is going to be what is referred to as a dehydration reaction. So in other words, you're literally going to remove water from where a hydroxyl group is. So that means the hydrogen has to go as well. So in order to form the most stable compound, you're going to have to remove a hydrogen from over here. So that would result in this kind of product formation. Okay, so again, that's not stereo specific because you have two methyl groups right here. Okay, so you've seen something similar to this before. We've used acid catalyzed substitution, but in this case it's going to be elimination because we have that heat there, which, by the way, that delta I didn't point out to you before is actually going to be just a generic indication that heat's been applied. Okay, for D, we have a bromo group there that's about a quaternary carbon, so if it splits off, it's going to be a tertiary carbocation, right? But can we get a more stable one? Yeah, actually we can. And since we're not applying heat here, there's going to be some kind of substitution. So we're going to get a product that's going to look like this. Okay, so that's going to stem from rearrangement and things like that. Not just with carbocation rearrangement, but also with proton transfer. Okay. Okay, and then you're also going to have a rearrangement where this is going to exist. As a product. Now, notice how this is a cis alkene. This is a tri-substituted alkene. So that should give you a little bit of an indication on what's going to be more thermodynamically stable. But also think about reversibility, particularly on this next step. Okay, so things that are irreversible tend to be kinetically favored. So what that means is at a lower temperature, things are just going to go and not revert back. Okay, so a bromo group is going to be really hard pressed to try to knock this and go in reverse under the same conditions. Okay. Now, with that said, so why don't you work through some of these mechanisms to get these two products and see if that reasoning kind of falls into place. What kind of thermodynamic product and what kind of kinetic product are you going to form? Okay, so for E here, we have the chloro group, which is obviously going to, well, not obviously, but in this case, nothing else here is going to be a very good leaving group. So in other words, that bromo group is going to coordinate, and it's all going to happen in one fell swoop. Why? Because we have an aprotic solvent, or polar aprotic solvent, which is going to stretch this dipole, right? So that bromo group comes in and substitutes. You're just going to get this product. Remember, there's going to be an inversion of configuration. Okay, it's not going to affect the stereochemistry of that methyl group that's hanging off over there. So is this going to be reversible? Well, they're kind of comparable in terms of being leaving groups and nucleophiles relative to one another. So if you were to imagine sort of I guess an energy diagram, they'll be somewhere close in terms of energetics, somewhere about relatively equal energy. Okay, so it can either go reverse or go forward if you're thinking about a particular energy diagram. Okay, so that's going to be the product that forms exclusively. And then the last one, so we have a bulky base here. So in other words, this T-butoxide, that's potassium terbutoxide, that's what the K stands for. That OT-BU, that just stands for T-butyl group, right? So in other words, this is a conjugate acid base pair. So OTS has to leave, that toxic acid has to split off, and then you're going to have carbocation, which is not going to be the most stable, so that is going to migrate over to where this carbon is hanging directly off of that phenyl ring. Okay, so your major product is going to be and just because I've shifted my electrons here, it doesn't make a difference. Okay. It's just resonated. Okay, so you're going to have a trans product, because remember that if it's cis, it's going to be less stable. Okay, so there's no indication of any type of heat here, but remember that this is going to be too bulky to substitute for something else. This is going to be too big of a group where things are going to collide and bounce off instead of coordinate. Okay, so this is going to be your major product, and we'll go over another set here and then call it a day for this module. Okay, so this next exercise is reasons for why the following transformations will not occur. So this is problem 9.84 in your text. Examples A through D. The first is seems somewhat straightforward, right? Because we just went over a particular type of dehydration mechanism. Now we have heat here. This is not sigma. Sorry about that. This should be a delta. It's a delta force. All right. So we have a strong concentrated acid. We have a little bit of water in there, so that means we're going to be under protic conditions. Okay. Now, which one is going to be, which oxygen is going to be protonated preferentially? Well, it's actually going to be this oxygen, right? So you can think of the inductive effect of these two carbons as opposed to this sole carbon stabilizing that resultant positive charge. So you're not going to actually see that particular compound. You're going to see something else. You're not going to see an ether. You're actually going to see the hydrolyzed counterpart. So it's going to look something like this. That's because you're going to actually split off that or hydrolyze that particular ether. So this is not what you're going to see for your product. For B, this is a little bit more straightforward. You have SH minus, which is going to be a strong nuke, a moderate nuke, but notice how it's, so sulfur is going to be a little bit less accommodating for holding extra electrons than, say, its isoelectronic counterpart of oxygen. So it's actually going to be relatively nucleophilic. And the big issue here is that bromo is on the other side here, so we're not going to see an inversion of configuration if we went from left to right. We're actually, what we're really going to see is not this dash bond, but you're going to see a wedge bond where both that thiol group, that SH is going to be what is referred to as thiol, is going to be on the same side as the chloro group. Okay. Okay, for part C, so we have an alkyne, so that means it has not exactly a protic hydrogen, but we have a strong base right there with NaH, so H minus is going to strip off that hydrogen that's terminal irreversibly. And then the second step, we're going to introduce this electrophile. But here's the thing, is that remember that proton transfer is going to happen the fastest. So what it's going to do is just basically revert it back to this. You're not going to see this product form at all. So remember that proton transfer is going to happen much quicker than coordination. Okay, so in other words, you're not going to see this at all. You're just going to see what you started off with. Okay. And then lastly, for D here, OTS is going to be the leading group that you want to boot off, presumably by an SN1 or SN2 substitution, or SN1 if it was under these conditions. The problem with this is that this anion is going to be fighting for this hydrogen as well. Okay, so they're going to be near the same pKa, which is going to be sort of an issue. So you're going to have some of this, you may have very little of this form, and maybe a lot more of this particular compound form instead. Okay, so that's a complication that would arise. Typically, if you're going to use something like that and you're going to do it under protic conditions, you would want to have the conjugate acid of that particular anion there. Okay, I hope that wasn't too much information to jam into your head within a couple hours, but you know, it's a lot of stuff to take in. So if you need to rewatch it, it's always going to be there. And I guess I'll see you guys in the next module. Thanks so much. Have a good one.